Hi everyone, so this is functional groups 1 to 4. Our first functional group is called the alcohols, and the alcohols are an OH functional group. The R here, as you can see, just means a carbon chain of any size. So we have 3 different types of alcohols. We have primary, secondary, and tertiary alcohols. Usually these little zeros are superscripted, so it looks like this. And I'm going to show you some examples so we can get an idea of what these look like. So our first type of alcohol I'm going to draw is a primary alcohol. So a primary alcohol is one that is on the end of a chain, and the OH is connected to a carbon, and that carbon is only connected to H's or maybe a single other carbon. The second example is a secondary alcohol, and the alcohol is attached to a carbon, and then this carbon is attached to 2 others. So this is what makes it a secondary carbon. It is in the middle of a chain. The last example is a tertiary alcohol, and this is the least common that you'll see. And this is when an alcohol is attached to a carbon, and that carbon is attached to 3 other carbons. So that one is probably the least frequent that we will see. What they all have in common is the OH, because that's what makes an alcohol. An alcohol is an OH functional group. Some of the properties and uses of alcohols is that they are all poisonous. So even the ones that we actually ingest are poison, and they're just less poisonous. But even hand sanitizer would be poisonous. It's used for lots of different things. Disinfectant, as you know, so hand sanitizer we're using a lot right now. And it's good as a disinfectant because it's a poison. So it will kill bacteria on your hands. And you can get poisoning from drinking too much alcohol because it is a poison. Now, things like paint thinner, fuel, hand sanitizer, preservatives, paint thinners, things like that, those are all more aggressive poisons, more aggressive versions of an alcohol that is poisonous. So those will often lead to blindness and death in a very short amount of time, a short amount of dosage, versus ethanol, which is the type of alcohol that you can drink, and you can drink more quantities of that without dying from it, but you definitely would feel the effects of it because it's a poison. In terms of naming, we are now going to take the parent name and we're going to change the ending. So in order to be an alcohol, think of the word alcohol. Alcohol ends with OL. That is the new ending for alcohols. We're going to number in front of the parent chain to say where the OH group is, just like we would with a substituent. And the OH group is the boss. So all the functional groups take the number 1 slot away from halogens, benzenes, anything else, multiple bonds. They are the top dog, so they're always going to get the lowest number. So just to give you an idea of how we would alter a name, let's say, for instance, I had a 4-carbon chain, which I would normally call butane. If I want to alter the ending, just the E is going to come off, and I'm going to add the new ending on. Sometimes it's hard to know how much of the ending to adjust, but we're just taking the E off, and then we're putting the new name ending on. So butane would become a butanol, for instance, to indicate that we have that OH group. So let's do this first example. So I've got a 4-carbon chain. So normally it would be a butane. I would number from the right-hand side to get to my alcohol the quickest. So this one would be a 2. Butane becomes butanol. So again, just like the previous slide, the E comes off, the OL goes on. Answer one more question. What type of alcohol would this be? A primary, secondary, or tertiary? If we have a look at the location of the OH, it's connected to a carbon that has 2 carbon neighbors, so this is a secondary alcohol. Let's give this one a draw. We have a 2,3-dimethylpentanol. So again, we'll start with pent, 5 carbons in a row. All means that OH functional group. Since there's no number in front of pentanol, that means it's in the number 1 location. And 1 can be left or right. You make the decision there. Based on the fact that I've got the OH on the far left, that means this will be my number 2, that will be my number 3, and I'm just putting some methyls on there. And then I'm putting in my H's so that everybody has 4 bonds. 2 more here, 1 more, 1 more, 2 more, 3 more, and then 3 each for those methyl groups. Let's get a little fancy with this one. Let's do 2 alcohol groups and see how we would name that. So again, we're going to start with that parent chain. We've got 1, 2, 3, 4, 5, 6. So normally that would be a hexane, but we want to change the ending to represent the fact that we have alcohols. We also want to represent the fact that we have 2 alcohols. So in terms of location, we've got a 2, 3 location. So let's start it off as a 2, 3 hexane. Remember the E comes off. Hexane diol. Di meaning times 2, OL meaning that OH functional group. And often we actually keep the E in here just for flow. Again, I wouldn't be too picky if you left it out, but that would actually be the better way of naming it, a hexane diol. There's also another way to name alcohols. Most functional groups just have one method, but we also have an alternative method, and this is handy if the alcohol has maybe another functional group at the same time. We can actually use hydroxy as a prefix. So this is when we would use the OH. So the OH is called a hydroxy as well. And this is, we would name it like a substituent, meaning out in front of the parent chain. So you can see the example here, a 2-hydroxy 3-methylpentane. Pent means, of course, 5 carbons. 1, 2, 3, 4, 5. 2-hydroxy means on the second location we're going to give it an OH. 3-methyl, 1 carbon. I'll put it down here. And then putting in our H's. So again, it's just an alternative method for saying the same thing. So you can have an OL ending to say it's an alcohol somewhere, or hydroxy tells you there's an alcohol somewhere. Our second group is the ethers, and its formula is ROR. So it's basically an oxygen between 2 carbon chains. The second R has a little dash, and that just means that the carbon chains could be different lengths, although they could be the same length as well. We'll see both. These ethers are very volatile, meaning as soon as you take the lid off the container, you can smell it instantly. It very quickly goes into the gas phase. And the reason why it's actually used as a gas in most cases is used as an anesthetic, and basically can put you out. It can put you to sleep, and it was the earliest anesthetic before they had IV anesthetics. And the picture you can see here is from a movie called The Cider House Rules, where they used that anesthetic to deliver babies, and so on. So anyways, it's a good anesthetic, but it's not as good as an IV where you can be put under for a certain amount of time. If your eyes started to flutter during surgery, they would put more ether onto your mask and you would breathe it in and go back to sleep. But sometimes you came out of your sleep when they were still working on your body, and sometimes you slept way too long after your surgery. So it wasn't an exact science. The other thing is, because it's so volatile, it actually would evaporate into the room that the surgeons were using, and so the surgeons would start to get drowsy as well. So they had to work in a well-ventilated area to make sure that didn't happen. It's also highly flammable, so you had to be careful around sparks or open flames. So not ideal. The naming rules are a little bit tricky for this one. So the short chain is considered to be like an attachment. It gets the O, and it also gets the name oxy. And then the long chain is like a parent chain, so it just gets a regular ane ending. So again, I might do something like this as a short form, just to give us an example, something like this. The short carbon chain gets the oxy, and the long carbon chain gets the ane. So that's a good way of sort of picturing what's happening. I can also take this oxy and put it somewhere along the chain. So you're going to see me do a couple things here. So let's do an example. So the O separates the 2 carbon chains. So I have 2 names here. One is the short carbon chain and one is the long carbon chain. So the shorter carbon chain gets the O and it gets an oxy ending. The longer carbon chain is considered the parent, so it just gets the ane ending, which we've seen before. So to put it all together, because I have a 2 carbon short chain, this is going to be an ethoxy. And then I have a 3 carbon parent chain, so it's going to be a propane. No space between the words. This one's a little bit different, so let's have a look at this. Again, we have short chain and long chain. So the shorter carbon chain gets the O, so this is the part that gets the oxy. There's my longer carbon chain, it's going to get the ane. Now, this one's a little bit tricky because the oxy is not on the end. It's actually moved to the second carbon of the parent chain. So if I were to number this parent chain, I would do something like this. So instead of just a methoxy, I'm going to call it a 2-methoxy because I have picked up that oxy and I've put it on the second carbon in the ane chain, and that is a butane, that parent chain. So you can see here that oxy is kind of like a substituent. It can move around. It can be attached not only to the end, but it can be moved so it's sort of in the middle of a parent chain as well. Our third functional group for today is the aldehydes, and an aldehyde is just a C double bond O, and it's always on the end of a chain. So we often show that H as being as a sort of separated, but you could write it with the H tucked in as well. I usually write it out. That's sort of the more common way of seeing it. And this double bonded O is called a carbonyl. It's a very common functional group. It's actually put together with other things as well, as we will see. This functional group is always on the end of a carbon chain, either the far left or the far right, because after an H, there's nothing you can attach to that. H only ever wants one bond. The aldehydes have really sort of strong odors. When they're small carbon chains, they have stinky ones, but as they get larger, they have really pleasant smells. So they can be used as preservatives, which is something like a formaldehyde, which has a stinky odor. It's just one carbon big. But the larger ones are really nice smelling, so essential oils, and in nature, things like vanilla, cilantro, cinnamon, these are all things that have aldehydes. When you're smelling those smells, those are aldehydes that you're smelling. The naming rules are really straightforward. You're going to give it an AL ending. So think of the word aldehyde starts with AL, the ending becomes AL. So again, just like before, let's say you have butane, and you want to show that it has a double bond O on the end. Again, just the E goes off, and it becomes a butanal. That's the new ending there. This will always be your number one carbon because the functional group, remember, takes numerical priority. So if the double bonded O is on the left, that's your number one carbon. If the double bonded O is on the far right, that's your number one carbon. Let's do an example. So here we have a carbon chain, and this will be the number one carbon. Notice that I just flipped the H to the left-hand side here just to get it out of the way, but I could also tuck it in. That would be fine as well. Because the C has a double bond, you only need one H here. So this is going to be a butanal, and I don't have to give a number, although I could put a number 1 if I wish, but really all I'm going to add here is a 3-methyl. Make a 3-bromopentanal. So again, pent means 5. 1, 2, 3, 4, 5. Al ending means that C double bond O on the end of a carbon chain. So we can put it on the far left or the far right. Doesn't matter to me. Wherever you put that double bonded O though, that now indicates your number one. And then the third one over would be like this. Now we're just putting in H's. So again, I like to flip my H out, but you can tuck it in if you like. And then we have 2, 1, 2, and 3. Last one is ketones for today. We have, again, that carbonyl functional group that you can see here, but this time that carbon is surrounded by R's, which means this is a carbonyl that is in the middle of the chain somewhere. So it looks like an aldehyde, but it's a locational. So an aldehyde has a double bond O at the end. A ketone is when the double bond is in the middle. Some properties: it's used as a solvent and an antibiotic. It's also found in pheromones, which are animal attractors. And it can also be formed when you have a lack of carbohydrates in your diet. And it puts you into something called ketosis, which is a situation where you actually create ketones in your body, and you can actually get them coming out of your saliva. The Atkins diet is one where you take carbohydrates out of your diet, and so you end up getting all these ketones built up in your body. The naming rules, just like the word ketone ends with the word "one," ketones also end with "one." We also are going to put a number in front because the double bond O will always be somewhere in the middle, unlike the aldehyde, which is always on the number 1. So we do need a number, and we're going to give it the lowest possible number as per usual. So same as before, if I have something like a butane, again, I'm going to take the E off, and it will become a butanone. So just the E comes off. Let's practice. here we have our parent chain running through the center. I'm going to number from the left-hand side because, again, I want to get to that functional group as fast as possible. We have a 5-carbon chain, so it will be a pentane normally. E will come off, one will come on, so it will be a pentanone. We also have to put the number in front, so it'll be a 2-pentanone. That tells us where that double bond is. And then, of course, we have to put in that substituent, so 3-methyl. Draw, so this one is a 2-phenyl 3-hexanone. So starting with hex, 1, 2, 3, 4, 5, 6. One tells us we've got that C double bond O. 3 tells us the location of that C double bond O. And then on the number 2, we've got a phenyl group, which is that benzene ring. And now we're just putting in H's. No H's for that double bonded O because we already have enough bonds there. Are the homework questions. Hurrah!